All right, couple more examples, and then we'll be done with this differential stuff, and then we're gonna move on for the very last little part here. I don't know how much we're gonna get through, but we're gonna start integral calculus, or at least get through kind of what the concepts are, and we're not gonna get a lot of to do much in the way of applications or anything, but at least we're gonna get a look at it, so you will have seen it. So let's look at this example here. You guys kind of talk me through this, please. If the masses of ball bearings produced by a manufacturer must be tightly controlled, so the volume of all the ball bearings with a radius of 3 centimeters, the volume can vary by no more than 0.012 cubic centimeters. What is the allowable variation in the radius of the ball bearings? Okay. So take a second. We got to make sense of that question. And I've done a little bit of, we've already done some of the work here. This is same derivative that we took last time, right? Okay, Seth, what do you think? Okay, good. So what are they asking for a relative? Yeah, in this case, they're not asking for a relative error, right? They're not asking for a percentage or anything like that. They want to know what is the variation in the radius, period. Right? We're not really concerned about how good is that, what percentage, we just want to know what is it? How much can the radius vary if the volume can vary by no more than 0.012 cubic centimeters, right? So what is it then? So somebody raise your hand out here and tell me, what am I trying to find? What do you think? I'm trying to find what is the allowable variation in the radius. So what's that going to correspond to? What's it going to look like in terms of like a variable or something? R is the radius. What's the variation in the radius? What is it? dr. There you go, right? It's dr, isn't it? Okay, right? Because what do we mean by variation in the radius? That's just error, right? What's the error in calculating the radius? What's the acceptable error? We can accept a variation, meaning an error, in the volume of plus or minus that much. Anything more than that, for whatever we're using these ball bearings for, that's the most we can handle. More than that, and they're no good, right? They're not going to work. Okay, so what can I do here then? And this is not a very hard problem, but you just got to wrap your mind around it. Yeah, here's the relationship we want, isn't it? Right? Because we're trying to solve for dr. Well, there's a dr, right? So we can just isolate dr. So if we isolate dr here, divide each side by 4 pi r squared, I just get dr equals dv divided by 4 pi r squared. So we know that r is 3, and that's dv. So what am I plugging in here? And try to be as precise as possible. What am I going to be plugging in for numbers? What am I plugging in on the top? Okay, yeah, can anybody improve that very slightly? Plus or minus, yeah, right? Because the air, it could be more or less by that much, the volume could. Okay, and that seems like a pretty minor thing, but I really like doing that, because then in my answer, look what we get. We get a plus or minus, which should be there, right? The radius could be either slightly too much or slightly too little, and whatever we get. So, well, that's, yeah, right. We get 12 on the bottom and 0.012 on the top. So that's gonna give us 0.001 over pi, essentially, right? Whatever that is. Okay, some number. And if we round it to, well, we could do it, but we don't even need to. Just plug it in the calculator and round it to however many decimal places we can, and that's our answer. Okay? Okay, give me thumbs. Yeah, yeah. Okay. Okay. All right, take another one. So here we've got this. This is the is a periodic motion equation in physics. So this is what we, for pendulum motion, this is the equation that relates the period, which is how long it takes to swing through one complete period. So one complete period would be like, that's not it, that's it, right? It's when I'm getting back to where I started. So if I'm starting right here, then it's when I get back to that starting position. So that's one period. L is the length of the pendulum, and what's little g? What do you think? Yeah, acceleration of gravity. You say right there, oh, okay, yeah. So if we did this, that's a kind of a pseudo constant on our planet, right? I mean, if you're close to the surface, if you're on the surface of the Earth, that's pretty much going to be constant, right? We usually just say 9.8 meters per second squared. It's close to that. It varies a little bit. If you're standing over something dense like basalt, it's going to be a little bit different than it would be if you were standing over something that's has less mass like water or sandstone or something. Or if you're up on top of a mountain, it'll be a little different than it would be if you're in the bottom of a valley, but very slight variations. Interestingly though, that is a way, by using a really accurate gravitometer, it's just an accelerometer, you can actually kind of get an image of what the Earth looks like beneath you. You can look at a density image by looking at the variations in gravity. And that's one way that geophysicists kind of try to make subterranean maps of what the crust looks like, what the substructure of the Earth looks like. Okay, so what are we told here? The pendulum has been subjected to an increase in temperature. So let's say it's made of metal, and the length increases by 0.5%. So we want to find the approximate percent change in the period. Okay? What are we going to do here? So what are we looking for? What's the look what, and when you're doing a question like this, you always want to kind of target the question. And what is the quantity that we need to fill in a blank for, right? I mean, what's the quantity we're trying to find? Yeah, approximate percent change in the period, right? Approximate means we're going to use our linear approximation, right? And that looks an awful lot just like a relative change in t, right? So that's going to be dt over t. Does everybody see that? That's the approximate change in the period. And the percent change just means we're going to compare it to the actual value and write it as a percentage, just a relative change to a percentage, okay? So we got to calculate that guy. So how are we going to do that? What are the pieces we need to do this? We've got t. What else do we need? I know what's on the bottom. It's that. But I got to calculate the differential, right? I got to calculate dt. So if that's t, let's calculate the differential. So what's dt? I want you to think about it. Everyone take a second, and why don't you just give this a little thought, maybe scratch something out on scratch paper. See if you can come up with something for this. How could I rewrite this in a way that's derivative friendly here? I mean, I could write it as t of L, but how could I rewrite, I'm talking about like the square root. How could I write that in a way that's going to be derivative friendly? 1/2 power. So I've got 2 pi times the quantity L over G to the 1/2. Okay. All right. What do you think? Natalie, well, how am I going to differentiate that then? How am I going to get dt? Okay, that just gives me pi, right? Good, so we get pi times, okay, good. So then we've got hand to the 1/2. You did that part, right? We bring the 1/2 out front. The derivative of hand to the 1/2 is 1/2 hand to the negative 1/2. So I brought the 2 out front. Now I've got to do hand to the negative 1/2. Okay. Last step. I got one more link in the chain. Because there's 2 layers to this, right? I've got a square root of some other function. So what's the last step then? Okay, yeah, I've got the derivative. Now I've got the derivative of hand, which is L over G. Do I need a quotient rule there? I don't. How come I don't need a quotient rule there? Because G's constant, right? G's just like any other number. It's a constant. So I've really just got L times 1 over G, right? So then the derivative of L is 1. And we just end up with 1 over G. But I'm writing this in differential form. So what has to be at the end? DL, right? Everybody get that? Because really all I've done is instead of writing it as dt dl, I've just multiplied both sides by dl. Put the dl over there, right? Okay, so we could clean that up a little bit. So dt equals, this is a negative square root, right? It's a square root on the bottom, not a negative square root. The negative 1/2 means it's going to the bottom as a 1/2 power. That's what a negative exponent is, right? So I'm getting pi times 1 over g is pi over g, we could combine those, times 1 over the square root of L over G, right, times dl. We can leave it like this. This is I'll put the dl in there. I'm just going to put that in the numerator. Okay, you don't have to do this, so don't let this confuse you, but there is one other little step I could do if I wanted to. What's the same thing as the reciprocal of, what about this part right here? I'm not going to try to say the words because I'll confuse you, but how could I change or simplify this part of the expression if I wanted to? Anybody know? Yeah, everybody see that? I could write this as the square root of G over L, right? Everybody see, did you see this? See how I could do that? Because really, this is on the bottom, this is the same thing as 1 over. I can always split up a square root. I've got a property of radicals that says if I have the square root of A over B, I can split it into separate square roots in the top and the bottom. So I could call that the square root of L over the square root of G. And what do I do if I have a fraction in the denominator? I just flip it and put it in the numerator, right? So everybody see, I could do that. Do I need to? No, you don't need to, but you could. So there's dt. Okay, we're trying to find dt over t. Okay, well now we've got dt, we've got t, so I should be able to maybe simplify this expression. If I do dt over t, what am I going to get here? Let's pick a different color. So dt over t is going to equal this thing in the numerator. So pi over g times, I'll write it as, I'll put the dl at the end. I don't need to. Either way, dl over square root of L over G. There's my dt on the top. On the bottom, I've got my 2 pi times the square root of L over G. I just have to simplify that, okay? Well, those are going to cancel, aren't they? Right? Everybody agree? Okay, now what do I do, though, if I won't do it yet? What do we do if we've got a complex fraction where I have fractions divided by fractions? Do you remember talking about this? I don't know. I know we've done this year. I know for a fact we did some stuff like this when we were simplifying limits of fractions, right? That's when we reviewed this a little bit. Do you remember the steps, though? If I've got a mess of fractions on the top and a mess of fractions on the bottom, what do I do? Yes, sir. Okay, right. Okay, but maybe to make that, I think your steps seem okay, but we can say it more simply. Don't I just flip and multiply by the denominator then? Right? I consolidate the top into a single fraction. One big fraction. Remember saying this? We get one big fraction on the top, one big fraction on the bottom, flip and multiply by the bottom fraction. Because then it becomes a product of fractions, which is easy to deal with. We just multiply straight across when we multiply fractions, right? So then we've got, if I do that, let's take those steps here. So I'm gonna go to the next page with this. How about? Oh, this is bad. It shouldn't be doing this. I feel like I'm this. Oh, this is bad. What's that? Oh, I saved it. Yeah. Okay, let me try. Yeah, you're right. You're right. That was a bad move. I think I can do this though. I think I can. Oh, there we go. Okay. I don't see. It's about to crash. I think it's doing weird stuff. This is a bad sign. Okay, so then on the bottom, I could treat this whole thing as being over 1. So then I'm just going to end up with whatever I have on the top, which is pi dl over g times the square root of L over G times 1 over 2 pi times the square root of L over G, right? So now we can see we get a little cancellation. Those guys cancel. And we get, on the top, I just end up with a DL. On the bottom, I get G2 times G times the square root times the square root. Undoes the square root, right? Times L over G. And now I've got an L over G on the bottom. I've got a regular fraction on the bottom. I could flip and multiply by that, right? And so I end up with DL over 2G times the reciprocal of that fraction, which is G over L. And look, the G's cancel. And all I'm left with is 1/2 times DL over L. Okay? Everybody see that? That's what the algebra tells us. But what are the math gods, or maybe these are the physics gods, I don't know, because it was a physics problem. What are the physics gods communicating to us here? dt, or dt over t, yeah. dt over t is equal to is equal to 1/2 times dl over L. That's a pretty important relationship. What's that tell us? How is the percent change in the period related to the percent change in the length? Yeah, it's half as big, isn't it? Everybody see that? dl, what's that represent? That's the percent change in the length, right? dt over t, that's the percent change in the period. So regardless of what the length and the period are, this doesn't even matter in this case, right? I mean, we're going to plug in some specifics to answer this question, but this is a pretty interesting relationship. When we extend the length of the pendulum, right? We lengthen the pendulum by any amount. We know that if there's going to be a change in the period and a change in the length, the change in the period is always going to be half as great, the percent change. The percent change in the period is always going to be 1/2 of whatever the percent change in the length is, corresponding to how much it lengthened, right? Okay, in this question, what are they actually asking for? They're asking for, okay, the length increases by 0.5%. Actually, yeah, so what is the percent change in the period? Percent change in the period would be half of that. So half of 0.5% is 0.25%, right? Okay. All right, what else did they ask? I can't remember. Oh, we're not going to worry about this. It says find the approximate error in this pendulum clock over an entire day. That's just a lot of math, just conversions. What would I have to do? What would I have to do there if I wanted to find out how much time are we how much time are we losing or gaining with our pendulum clock over an entire day? How much is the what's the cumulative error going to be over a day? What would I have to do? Yeah, I'd have to take, right, if I wanted to know, I'd have to see, okay, well, if I know what dt is for one period, I would have to multiply that by, I'd have to figure out how many periods there are in one given day, right? Does that make sense? Okay, so I know, I mean, we won't go through all the math on that. There's just kind of a conceptual question. But if I know that dt over t equals 0.025%, and I can calculate that the period is, error in the clock. Okay, so I would have to then do what? If I know that this is the amount of error, I'm not sure you can actually do this because we don't know the length. So you can't actually do this one. So it's a good thing we didn't try to do it, right? Everybody see that? Because we would have to be able to know, for us to be able to do this, we would have to know what is the length of one pendulum swing, right? And then just figure out how many of those are there in a 24-hour day, and then multiply that dt by whatever that number is. But that's not calculus. We can skip that stuff. How about last one here? The maximum allowable percent error in computing the area of a circle cannot exceed 3%. Okay? Estimate the maximum allowable percent error in measuring the circumference. Okay? So take a second and think about that one. Everyone, just try to wrap your head around that for a sec. Give you a couple minutes. Scratch out, see if you can come up with what is it that we're trying to find, and you got to come up with some kind of a relationship here between area and circumference. So that's not a calculus issue, but see if you can do that real quick. What's that mean? Let's write that mathematically. Percent error in computing area. What's that going to look like? dA over A, right? Okay. So dA over A cannot exceed 3%. Okay, but what's the relationship? Is it equal to? Less than or equal to 0.03, right? And it really is kind of weird to put a plus or minus there, but we know we don't know if it's plus or minus at this point, right? So we really could kind of think, okay, well, it's plus or minus, right? There. Okay, good. But now we've got to somehow come up with the maximum allowable percent error in measuring the circumference. So what's that going to look like? What's that going to look like? Yes, sir. Right, but okay, but what am I trying to find here? Right? Percent error in circumference has to just be dc over c, right? So somehow we've got to figure out what that is. We've got to be able to come up algebraically after we do the calculus. We've got to be able to solve for dc over c, okay? So what is the relationship? We got to come up with the relationship between area and circumference. Well, how are we going to do that? We know area of a circle as a function of r, right? It's pi r squared, okay? This is a good problem. This forces you to think about things a little differently. So if I want to be able to write this in terms of circumference, think about this in terms of what the math steps are going to be. I want to make a substitution, don't I? Everybody see that? I want to be able to substitute my r for a c here, for some c's, right? An expression in terms of c that I can plug in for r. So I need a secondary equation then that's going to relate the r and the c, right? So I can make that substitution. Well, what is that secondary equation? What's the relationship between c and r? C equals what for a circle? 2 pi r. So what am I going to do with that secondary equation? Yeah, I'm going to solve for r. All right, I'm going to get r equals c over 2 pi, put a box around it because that's my substitution equation, okay? It helps when you get to a point in math where you can kind of start to talk about things in terms of concrete processes that we've done before. It makes it easier to iron out your thinking, right? Organize your thinking on this. So then we end up with A is equal to pi times the quantity C over 2 pi squared. And so what do we just get there? We get pi C squared over 4 pi squared. And I can cancel a pi, top and bottom, right? And so I get A as a function of C is equal to C squared divided by 4 pi. Okay, now what? Yeah, I need to calculate the differential, don't I? Because I'm trying to build this expression, dA over A. I know what A is. I have A in terms of C, but now I need to get dA in terms of C. Okay, so let's see, Amber, what am I going to get if I calculate dA? What am I going to get over here? Okay, you're doing quotient rule, right? Okay, but we don't need to do quotient rule here because the bottom is a constant. So I could just think of it this way. I'm thinking about this as being a 1 over 4 pi is my constant times c squared. Just use a power rule, okay? So what's that going to give me? Good. Times 2c, there you go, good. 2c, what's the last step if I'm writing it in differential form? What's the last step? Anybody? dA equals 2c over 4 pi dc, right? Because I'm just taking that. I would have been what you calculated was that dA dc, right? You calculated the derivative of A with respect to C, but we're just multiplying each side through by dc. Okay, now we've got our two ingredients. We've got A and we've got dA, and so we can write dA over A as the quotient of those two expressions. On the top, I've got 2c, oh, actually, let's do that. Let's make that a 2, cancel a 2. So I've got, on the top, I've got c dc over 2 pi, right? On the bottom, I've got a, which is this, c squared over 4 pi. We flip and multiply by the bottom, and we get c dc over 2 pi times 4 pi over c squared. And now all the magic happens, right? Now we get tons of cancellation. The pi's go away, we cancel a c, and once again we get something like, I've got a 4 over a 2 reduces to a 2 times dc over c, right? Well, look, we got a relationship here then. dA over A is equal to 2 dc over c. So we can just make this substitution. We can substitute all that stuff in our original equation, because that's what dA over A was equal to, right? So I get, this becomes 2 dc over c, that's what dA over A is less than or equal to I better save this. I just feel like I'm going to get right to the end and this thing's going to crash and I'm going to lose all my work. Is less than or equal to my plus or minus 0.03. Well, what's the only thing I have to do? Divide by 2, right? Divide each side through by 2, and I end up with dc over c is less than or equal to plus or minus 0.015 if I divide by 2. Okay, so then what is the maximum allowable percent error in measuring the circumference? 1.5%. Okay, so if we want to restrict, if the error in computing the area of the circle can't exceed 3%, then the error in measuring the circumference can't exceed plus or minus 1.5%. Okay, give me thumbs. Okay, all right. That's all I got for you. When are we out of here? 5 minutes.